Hello friends, I welcome you to my third lecture on Cauchy type integral equations. We in the last lecture we considered Cauchy type integral equation of the first kind. Now we shall try to solve the Cauchy type integral equation of the second kind. So let us consider the inhomogeneous singular integral equation. Inhomogeneous, or we can also call it non-homogeneous singular integral equation. So consider the non-homogeneous singular integral equation GS equal to Fs plus lambda times integral 0 to 1 gt dt t minus s, where this star indicates the principal value of the Cauchy principal value of the integral. So to solve this singular integral equation, we first reduce it to a Volterra type integral equation, and then the way we solve a Volterra type integral equation, we shall solve it. Now let us so to do this we will need this identity, integral 0 to u dt upon u minus t raised to the power 1 minus alpha t to the power alpha into t minus s equal to pi cot alpha pi over u minus s to the power 1 minus alpha s to the power alpha when 0 is less than s less than u minus pi cosec alpha pi over s minus u to the power 1 minus alpha s to the power alpha whenever u is less than s. So let us recall that in the first lecture on Cauchy type integral equations, we had shown that minus integral 0 to u minus s over s to the power alpha ds over u minus s into s minus t is equal to this expression when 0 is less than t less than u, and it is equal to this when u is less than t. And there I had shown that integral 0 to infinity xi to the power alpha minus 1 d xi over xi plus 1 is equal to pi over sin alpha pi by putting xi equal to t upon 1 minus t. Now here but we had not done this integral 0 to infinity xi to the power alpha minus 1 d xi over xi minus 1. So I will now show you how we can calculate the integral 0 to infinity xi to the power alpha minus 1 d xi over xi minus 1. Now we have to show that if you compare the two values, you have to see that you can see that integral 0 to infinity xi to the power alpha minus 1 d xi over xi minus 1, we have to prove that it is equal to minus pi cot alpha pi. So we have to show this integral 0 to infinity xi to the power alpha minus 1 d xi over xi minus 1. This is equal to minus pi cot alpha pi. We can say that we have to prove that integral 0 to infinity, for convenience we can write in place of xi we can write x. So x to the power alpha minus 1 dx divided by 1 minus x equal to pi cot alpha pi 0 less than alpha less than 1. Now we shall find this integral, this real integral, by using the contour integration. So what we will do is, so first we shall prove this lemma. If AV is the arc alpha less than or equal to theta less than or equal to beta of the circle mod of z minus a equal to r, we know that in the complex plane mod of z minus a equal to r represents a circle whose center is at the complex number a and whose radius is r. So then if limit z tends to a, z minus a into fz is equal to k, where k is a constant, then we have limit r tends to 0 integral over ab fz dz equal to I times b minus alpha over k. This result we will use when we evaluate this integral by contour integration. So let us see how we prove this. So this is the center and r is the radius. So this is mod of z minus a equal to r. So AB is the arc of the circle mod of z minus a equal to r, and the arc AB of the circle lies between the argument theta that is alpha less than or equal to theta less than or equal to beta. So this is alpha angle, this is alpha, and this is beta angle. Now we are given that limit z tends to 0, we are given that limit z tends to a, z minus a into fz is equal to k. Or we can say limit z tends to a z minus a into fz minus k is equal to 0. So, by the definition of limit for a given epsilon greater than 0, there exists a delta greater than 0 such that mod of z minus a into fz minus k is less than epsilon whenever 0 is less than mod of z minus a less than delta. Now, we have to show that as r goes to 0, integral over ab fz dz equal to I times beta minus alpha into k. So, when r goes to 0, we can take our r to be smaller than the number delta. So, let us choose r So, let us take r to be less than delta. Then we have this inequality whenever 0 is less than mod of z minus a less than r, and we are taking r to be less than delta. So, mod of z minus a equal to r, mod of z minus a equal to r circle will lie inside the disk. This is mod of z minus a equal to r, it will lie inside this disk. This is delta radius, this is r radius. So, this is a center. So, this inequality, so the inequality 1 will be valid, then the inequality 1 will be valid on the arc AB of the circle mod of z minus a equal to r. Now, let us write integral over AB fz dz equal to integral over AB z minus a into fz minus k plus k divided by z minus a into dz. Now, this integral can be expressed further as, we can break it into two parts. Z minus a into fz minus k upon z minus a into dz plus integral over AB k dz upon z minus a, and let us denote them by integral I1 and I2, the two integrals. So, first let us estimate the value of the integral I1. Okay. So, let us see mod of I1 is less than or equal to integral over AB mod of z minus a into fz minus k upon mod of z minus a into mod of dz. On the arc AB, the inequality 1 is valid. So, mod of z minus a into fz minus k can be made less than epsilon. So, less than epsilon, and AB arc lies on the circle mod of z minus a equal to r. So, we have r here into mod of dz. Now, on the arc AB, mod of z minus a equal to r I can write in the parametric form z minus a equal to r e to the power I theta. So, dz equal to r e to the power I theta into d theta. So, this is equal to, and for the arc AB, theta varies from alpha to beta, this is given to us. So, integral over alpha to beta epsilon over r into mod of r e to the power I theta into d theta. So, this is integral alpha to beta epsilon over r into r d theta, which is equal to epsilon times beta minus alpha. Now, since epsilon greater than 0 is arbitrary, we can since epsilon greater than 0 is arbitrary, we can make it as small as we please, and therefore mod of I1 can be made as small as we please, and so we have I1 equal to 0. And thus integral over AB fz dz is equal to I2 when r goes to 0. So, thus when r goes to 0, integral over AB fz dz is equal to I2, which is equal to integral over AB k times dz upon z minus a. Again, let us use the parametric representation of the arc AB. So, then we have integral alpha to beta k times r e to the power I theta into I d theta divided by r e to the power I theta. The arc AB, let us recall that the arc AB lies on the circle, mod of z minus a equal to r, and so we can put z minus a equal to r e I theta and dz equal to r e I theta I d theta. So, this cancels, these two cancel each other, and thus we have I into k beta minus alpha. So, thus we have when r goes to 0, integral over AB fz dz tends to I into k times beta minus alpha. So, this is the lemma which we will use to evaluate this integral, this real integral, by using the contour integration. So, what we do is, let us consider the contour integral over C fz dz, where fz is equal to z to the power alpha minus 1 over 1 minus z. So, integral over z to the power alpha minus 1 over 1 minus z dz. Now, what is C? C is the closed contour consisting of the real axis So, C is the taken, so the integral is taken around the closed contour consisting of real axis from minus r to r, and upper half of the large circle mod of z equal to r. So, this is origin, this is mod of z equal to r, this is the upper half plane, this is x axis, this is y axis, and we move in the counterclockwise direction along the semicircle of radius r with center at the origin. Now, let us look at this. This is nothing but since alpha lies between 0 and 1, we can write that as z to the power alpha dz divided by z into 1 minus z. Therefore, z to the power alpha over z into 1 minus z has singularities at z equal to 0 and z equal to 1, which lies on the real axis. So, one singularity lies here, z equal to 0, and another singularity lies here at z equal to 1. We remove these two singularities by indentation, and what we do is we take semicircles of radius small r and small r dash. So, let us draw a small circle here of radius r. This is r radius, we call it circle CR, this semicircle CR, and here we take another semicircle with center at z equal to 1 of radius r dash, and we call it CR dash. Now, when we start moving along the semicircle in the counterclockwise direction, when we reach here minus r, we move along the real axis. When we come here, this is minus r dash. So, when we come here, we move along the semicircle in the clockwise direction. When we come here, we move along the real axis, and then again we move along the semicircle in the counterclockwise direction. When we come here, we move along the real axis and reach r. So, now this contour C, which consists of the semicircle from r to minus r, then from minus r to minus r dash, from then along CR, then from r dash to 1 minus r dash, this is 1 minus r dash, this is 1 minus r dash, this is minus r dash, this is minus r, and then this is r, and when we reach here, this is 1 plus r dash. So, it becomes a simple closed curve. When we move on the semicircle, let us say call it as gamma. When we move along the semicircle gamma, then the real axis from minus r to r, then along semicircle CR, then from along real axis from r to 1 minus r dash, then from 1 minus r dash to 1 plus r dash along the semicircle CR dash, then from 1 plus r dash to r. When we move, we are moving along the simple closed curve in which the function fz is z to the power alpha over z into 1 minus z is analytic. So, by Cauchy integral theorem, integral over C z to the power alpha dz divided by z into 1 minus z will be equal to 0. Now, this is integral over gamma, we can break it into parts. Plus integral over, now when we have moved along gamma, when we reach here minus r, from minus r to minus r we move along the real axis. So, z becomes equal to r. So, minus r to minus r x to the power alpha over r, you can write x to the power alpha minus 1 upon 1 minus x dx. Then we are moving along CR in the clockwise direction, CR x to the power, this is z to the power alpha minus 1 upon 1 minus z dz, and then we are moving along from r to 1 minus r dash, from r to 1 minus r dash, x to the power alpha minus 1 upon 1 minus x dx. Then we are moving along CR dash in the clockwise direction, after we reach this point, we are moving along the real axis again from 1 plus r dash to r. So, this thing is equal to 0. Now, what we do is, let us evaluate the integral. First, we are estimating the integral along gamma, integral over gamma z to the power alpha dz upon z into 1 minus z. So, let us see integral over gamma z to the power alpha minus 1 dz upon 1 minus z. Let us take mod of this. This is less than or equal to integral over gamma mod of z to the power alpha minus 1, then mod of dz, and mod of 1 minus z. Mod of 1 minus z is greater than or equal to mod of z minus 1. So, we have mod of z minus 1 here. Along gamma, mod z is equal to r. And 0 is less than or equal to theta, less than or equal to pi, because we are taking the semicircle. So, this is equal to integral 0 to pi, and we have here r minus 1. This is mod of z to the power alpha minus 1. So, we get r to the power alpha minus 1, and then mod of dz. Dz is z is equal to r e to the power I theta. So, dz equal to r e to the power I theta d theta. So, mod of dz will be equal to r d theta. So, this is r to the power alpha divided by r minus 1 into pi. R to the power alpha divided by r minus 1. Now, when r goes to infinity, okay, when r goes to infinity, since alpha is less than 1, okay, r to the power alpha over r minus 1 will go to 0 as, so this goes to 0 as r goes to infinity in view of 0 less than alpha less than 1. So, when r goes to infinity, integral over gamma z to the power alpha minus 1 over 1 minus z dz goes to 0. Now, let us evaluate the integrals over CR and integrals over CR dash. Okay. Now, integral over CR, when we evaluate integral over CR, we have z to the CR is the this is 0, this is 1, and this is our gamma, this is CR, and this is CR dash, this is minus R, this is R, this is 1 minus R dash, this is 1 plus R dash, and this is R. Now, here what we have, this is the indentation along with 0 as center. Okay, so let us use the lemma. In the lemma, what we have said, if AV is the arc, alpha less than or equal to theta less than or equal to beta of the circle, mod of z minus a equal to r. So, CR is the arc of the circle, mod of z minus 0. CR is the arc of this circle, mod of z minus a equal to r, where 0 is less than or equal to theta less than or equal to pi. Let us see the limit here. So, limit z tends to a means z tends to 0, because it is the circle with center at 0. So, limit z tends to 0, z minus a means z times fz. So, this is left limit z tends to 0, z into z to the power alpha minus 1 divided by 1 minus z. So, this is limit z tends to 0, z to the power alpha divided by 1 minus z. Now, alpha is positive, it is greater than 0, less than 1. So, this limit is 0 as z tends to 0. So, k is equal to 0. This means that integral over CR, integral, so thus integral over CR z to the power alpha minus 1 upon 1 minus z dz is equal to I times beta minus alpha, that is pi minus 0, k is equal to 0 here. So, into 0 equal to 0 as r goes to 0. So, when this radius of this circle CR goes to 0, this integral goes to 0. Similarly, let us evaluate the other integral. Similarly, integral over CR dash z to the power alpha minus 1 upon 1 minus z dz. This will be equal to I times pi minus 0 into k as r dash goes to 0, because the radius here is r dash. Now, let us evaluate k, where k is equal to limit z tends to a. Here the center is at 1, the circle is of radius r dash centered at 1. So, CR dash is mod of z minus 1 equal to r dash, where 0 is less than or equal to theta less than or equal to pi. So, limit z tends to 1, z minus 1 into fz. Fz is equal to z to the power alpha minus 1 divided by 1 minus z. So, this will be equal to, so this is minus limit z tends to 1 so this will cancel with this, we will get minus 1 z to the power alpha minus 1. So, this is equal to minus 1. So, we get here minus I pi. Thus, limit r dash tends to 0, integral over CR dash z to the power alpha minus 1 divided by 1 minus z dz is equal to minus I pi. Now, let us recall that, let us put the, so let us now in this equation, let me call this as equation 1. In equation 1, let r go to infinity, this capital R go to infinity, and small r and r dash go to 0. So, letting r go to infinity, r comma r dash go to 0 in equation 1. So, when r goes to infinity, this goes to 0, this integral goes to minus infinity to 0. So, we have minus infinity to 0 x to the power alpha minus 1 divided by 1 minus x dx. Here, now this when r goes to 0, integral over CR z to the power alpha minus 1 into over 1 minus z dz goes to 0. Here what we have, integral over 0 to 1 x to the power alpha minus 1 upon 1 minus x dx. Then here when we are moving around CR dash, we are moving in the clockwise direction. So, with the value of this integral, we put minus sign. So, minus of minus I pi, and then we have integral over 1 to infinity. So, this is what we have. Now, let us simplify this. So, we can write it, now we have minus infinity to 0, then integral 0 to 1 and then integral 1 to infinity. We can combine and write integral over minus infinity to infinity x to the power alpha minus 1 over 1 minus x dx plus I pi equal to 0. We can say integral over minus infinity to 0 x to the power alpha minus 1 upon 1 minus x dx plus integral over 0 to infinity x to the power alpha minus 1 upon 1 minus x dx equal to minus I pi. Let us now change the integral minus infinity to 0 to infinity. So, integral over minus infinity to 0 we may write integral minus infinity to 0 x to the power alpha minus 1 upon 1 minus x dx equal to infinity to 0 minus y to the power alpha minus 1 minus dy divided by 1 plus y by putting x equal to minus y. Now, this is equal to minus times minus 1 to the power minus 1 okay, minus 1 to the power alpha minus 1 minus 1 to the power alpha we may write. This is minus 1 to the power alpha by dy by to the power alpha minus 1 dy upon 1 plus y integral 0 to infinity, and we put a negative sign when we change the limits of integration. So, this is equal to minus e to the power I alpha pi. We know that e to the power I pi is minus 1. So, minus 1 to the power alpha we can write as e to the power I alpha pi, and integral 0 to infinity by to the power alpha minus 1 dy over 1 plus y, we know the value of this pi over sin alpha pi. So, let us put this value here. So, we will then have integral over 0 to infinity x to the power alpha minus 1 upon 1 minus x dx, and then let us put the value of the integral. So, minus e to the power I alpha pi into pi upon sin alpha pi equal to minus I pi. So, this is equal to integral 0 to infinity x to the power alpha minus 1 upon 1 minus x dx, and here I can use the Euler's formula. So, pi upon sin alpha pi, and then e to the power I alpha pi I can write as cos alpha pi plus I sin alpha pi. So, this is equal to minus I pi. Now, when you multiply minus pi sin alpha pi here, then you see that sin alpha pi will cancel, minus I pi will cancel with minus I pi, and we will get integral 0 to infinity x to the power alpha minus 1 dx divided by 1 minus x equal to pi cot alpha pi. So, this is how we show that integral 0 to infinity x to the power alpha minus 1 upon 1 minus x dx is equal to pi cot alpha pi. So, this is the proof. We will make use of this in getting the solution of the Cauchy integral equation of the second kind. So, that we will do in the next lecture. So, with this I would like to conclude my lecture. Thank you very much for your attention.